Hello, everyone. Welcome to the first session of quantum computing from zero to hero. I'm really glad that we start to join us for this sessions because here we're going to talk a lot about a lot of pretty cool stuff that's happening around the world and about a future that is very promising in especially when you considering what this amazing quantum computer is going to do for us. So my name is Elias Hassani. I am the cybersecurity instructor in the Saskatchewan Polytechnic in Canada, and also I am a PhD student working on PQC or post-quantum cryptography and quantum cryptography at the University of Saskatchewan. There are a lot of great areas in research that we're going to discuss about in this series as well, especially for those of you who are interested in getting to academia and doing more research work. I'll explain to you what are the state of the arts and what type of research might be more interesting. And also I'll discuss about some opening positions that are available within Canada, Europe, and US, and some other parts of the world. So let's get a little bit to the history, like where started all these things. I'm gonna go a little bit. Let me still get a little bit back. I'm gonna show you a Wikipedia page here, and I'm gonna show you a little bit of history about Charles Babbage. If you don't know him, you should. He actually built the first mechanical computer, and that was back in 1820s. So if you look at the model of the machine and the computer that he could build, I'm going to scroll down here as you see a portion of the difference engine that he built, and he was able to do some polynomial computations on it. So if I show you a little bit better the computer itself, I think there should be a very nice images here and pictures. You see here is a part of the Charles Babbage difference machine. And it was basically, again, to automatically find some arithmetical operations. So why I'm explaining about this, I'm just going to say like all the innovations and all these breakthroughs starts very way back in history. Usually, when we realize that something is already accessible, but everyone, let's say about AI, then most of the people realize the real power back in, let's say, 22, 23. And before that, of course, a lot of researchers work on that, but the public population didn't work much with that. But then with the introduction of AI chatbots, people finally see that. So we expect to see the same trends for any other technologies too. Of course, it always starts with academia and with a lot of researchers who spend days and nights on things that nobody understands and nobody believes them until finally you see it on the market. So let's go a little bit further into the history. And the picture that you are seeing here is the first it's kind of one of the mechanical computers that IBM was using back in 1949. So this was using vacuum tubes, and you see that very big computers. There was no transistor back then, but still they did a lot of interesting equations and mathematical calculations on them. And of course, before then, even about the abacus, that of course people use that in the smallest stores for doing some calculation regarding how much you have to pay. So we go a little bit further into the history and we get to the transistor, which was a really huge breakthrough that made it possible to do the transition from the mechanical computers to electric computers. And this all dates back to 1948. And you probably know already John Bardeen, William Shockley, and Walter Brattain that who worked at the Bell Labs. So now we saw that, okay, we have a device that is like a switch that by providing the electric current, we can turn it on and turn it off. So later on, we go a little bit further, and this is actually one of the early electronic computers, and that you see in the Pennsylvania Museum. And this also, you see that it dates back to 1948. And a little bit, still going further, I'm going to go through the history now. We get to the integrated circuits. So integrated circuit actually then made it possible to provide a lot of transistor within a smaller space. So with one transistor, you cannot do really much. You just can turn on and turn off a light. But with thousands, with million, and finally with billions of that, you can do a lot of super cool stuff that we are doing today. So this was done around 1960s, and that actually was the other breakthrough that made it possible to build larger scale classical computers, electronic computers that we are using today. So IBM is back then was one of the leaders in this field, and still they are, of course, one of the leaders, and I would say like probably the most important leader here, because they are one of the they are at the forefront of a lot of innovations. Not that other one are not important, including what our research are done by Microsoft, by Google, by IonQ, and Pascal, and many other companies that are actively doing a lot of great research in this field. But this is let's look at one of the pictures that IBM has published on their library. And you see, like, this is like the chandelier style that you see. And you might wondering why these are so big computers here. But actually, the quantum computer itself is not very big. It's pretty small. But you see all this stuff around it are mainly for cooling. Because we'll discuss it later that for a classical computer that you're running right now, like your laptop, they can operate in the room temperature. Of course, if the temperature increase significantly, let's say become 40, 50 degrees, then it starts to slow down and finally might stop working. But a classical computer needs a very extreme cold condition. We are talking about near 0 Kelvin. So now you might wonder what would be the size of the quantum processor inside this computer. I'm going to show you one picture by Microsoft here and here. So this is one of the quantum chips that is developed by Microsoft, and you'll see quite similar also for IBM and other manufacturer. I mean, the shape might change a little bit, might be a circle or triangle, rectangle, but anyway, at the end, they are the same. So here you see that we have this chip that we have a couple of qubits on it. Okay, let's get back to the slides. But why now we get to the question, if we have a lot of great computers, and we have supercomputers that they are doing a lot of great stuff for us. Even we have GPU today that they run our machine learning algorithm, and they are running the large language models. So why do we need to switch to quantum computers? So there are a couple of reasons. One of them is about the Moore's law. I'm going to get back to these pictures that I've got here. So Moore's law, saying that the number of processors within the computers is doubling every 18 months to 2 years. So if you look at it, actually, that rule been true since 1968 and 1970s. And you see a linear line here. I'm gonna if you just look at this line here. So you see a linear line that is going up, but also you see that it's starting to flat out. So here you see first it was linear, and now it starts to go towards flattening out. So what is the reason behind this? The reason is that the transistors are becoming smaller and smaller. We are talking about the size of few atoms, let's say 5 atoms or 6 atoms. So when you get to such a scale, such a small number of atoms that are together tight, So that creates a lot of issues. For example, that can create a lot of disturbance, a lot of heating issues, and they start to show some quantum physics behavior. For example, one of them is quantum tunneling behavior that we're going to discuss about it a lot in the future. But I would just want you to know that when the number of the atoms become compressed, like they becomes closer and closer to each other, this creates a lot of issues, including for heating as well. So this is not the only reason. The other reason that is very important for you to know is that nature is not classicals. And there are a lot of problems that still we are not capable to solve, even with the best supercomputers in the world. For example, if you want to simulate in chemistry, like a behavior of a molecules, it's a very hard problem to simulate this type of problem in a classical computer. Because you need to consider a lot of possibilities here, and you need a lot of bits to be able to store this event. And sometimes it becomes impossible after a while. Even if you want to simulate the molecule of water, H2O, becomes a very, very huge problem in a classical computer, so that you cannot really properly show uh, and do a exact replica of a water molecule. But in quantum computer, in fact, this is a very easy problem because we are dealing directly with atoms. So with a few qubits, you can solve this and you can simulate the behavior of molecules. So why this matters? The reason is that if in chemistry or in drug discovery, we can create simulate the behavior of the like let's say how a drug can affect your body, we can actually simulate the entire body molecules of the body and DNA, RNA, and everything, and then see how it's going to impact the body. So we don't need to wait for, like, let's say 2 decades or 3 decades to test the new drugs for cancer. So that's going to help us a lot. And also you don't need a lot of people to do trial on them. So that creates also solved an ethical side of things. But this is not about chemistry and not about healthcare. It comes to many other type of problem. One of them is logistics problem. Let's say if you have 1,000 trucks and you're finding the best way to route that traffic, then the number of combination becomes much greater than the number of atoms in the universe. This is a very, very huge problem. You might think that doesn't look like a big deal if you have 1,000 trucks and you want to find the best way to route the trucks, but it is actually, and it is impossible almost to solve such problems in a classical computer. And a lot of this mail delivery companies, for example, Canada Post, let's say, or FedEx, UPS, and etc., they are dealing with a lot of optimization problems here, how they can route their traffic to find the best path for getting to the destination. For example, I know that some of them try to have, I think it's for UPS, that they have a rule that truck drivers always have to turn right, because they say if you have to turn left in an intersection, you have to wait for the traffic light to become green. So that creates more the waiting time and also more risk of accidents. So I'm just saying, like, but of course that is helpful, but that is not the ultimate solution. Now, if you can save, let's say 10% or 20% in time, that means 10% or 20% in fuel. And that creates a lot of opportunities for a greener environment. So we don't need to create a lot of air pollution, and also a lot of cost will be saved by the reduction in fuel. And this is another example. There are many, many other problems that we can solve. For example, a lot of airlines they also have the same issue, like for rescheduling flight, for weather forecasting, when the flight might be actually canceled, or for agriculture, what is the best time for cultivating your crops. It can be very unpredictable, and it's a very hard problem again for your classical computer to solve such problems. And you can save a lot of money by doing the yield for agriculture or yielding the crops at the right time. What else we can think about? We can do also any type of optimization. One of them is machine learning itself. For machine learning, we have to do a lot of trial and error until we find the best weight for the neural networks, right? So and this type of, or for SVM, support vector machine, in the machine learning algorithm also is about a lot of training. But we can reduce the time of training by using the quantum annealers and quantum computers. But if you don't know what is a quantum annealer, don't worry about it. I'll talk about it in the second session. But just know that we can solve those optimization problem very efficiently. And again, for those people who are designing cars, who are designing airplanes, they can do a lot of tests for checking the turbulence, for checking the design to see what type of material they should use. Another very cool example is for battery design. You see, batteries are not keeping the energy for a long time. Like, that's still a very big limitation in the electric cars. But what if we can design electric cars that they have a battery that lasts for a much longer time? So that's something very valuable. And so this is just a limited list that I really set, and these are very huge bottlenecks when it comes to classical computers that your quantum computer is able to solve. There is one quote from Richard Feynman that I really love, and I like to just read it out loud here, that he says, "Nature isn't classical. Damn it. If you want to make a simulation of nature, you'd better make it quantum mechanical." If you look at it, it's actually very powerful. It's powerful thing that Feynman said, because still with the power of AI and machine learning, we are doing great stuff, but we are still using transistor. We are using still the classical computing concept. No quantum mechanical. Nature is quantum mechanical. Everything is built upon molecules, atoms, and that. So if you want to simulate the atoms in the right way, you have to use atom for the simulating itself. So let's say if you have solar panels and that you want to absorb the sun and convert this to, like, whatever the photosynthesis is doing the same process, right? Converting the sunlight to energy for the plant. And now we are doing the same in solar panels. We are converting the sunlight to the energy that we can harvest. But still we have limitation. For example, the first solar panel that they built had an efficiency around 1%. But of course, we've done a lot of advancement in this field, and now we can get around 50% of efficiency. But what if we can create 90% of efficiency? I mean, by understanding how, for example, plants are absorbing the photons in the light. So that's another problem that we can solve. So just to clarify something, a lot of people might think that a quantum computer is just a super CPU that is paralyzing everything. Don't get mistaken, it's not actually a GPU that can paralyze all your stuff, because for that task already we are using GPUs. But actually, it's just a different way that is solving, and it has nothing to do with it has something to do with parallel processing, but it's not just a super powerful CPU out there. One way that we can look at it actually is quantum. Let me get back here, and then I'll go here, and then we'll continue. Is quantum maze problem. This is like a maze problem. Let's say if you have a maze and you have a mouse that's gonna enter from the entrance and exit from the other side. So the mouse will try to all the possibilities. Okay, like sorry, I'm gonna figure out where's my pen here. Okay, I got it. So here's the entrance and here the exit. So the mass will start to go through different direction, this direction, and start to see finally how can get out of this maze. But if you're using, this is like a concept of classical computer. We try every possibility until we find the exit, right? But in a quantum computer, we are going through all the possibilities at once. Why? Because quantum computers have a feature that is called quantum tunneling. And we're going to discuss about it later, that can actually try all these paths at the same time. So that is super cool. And you'll see how it's even possible. Yeah, I don't need to remove that anyway. Let's continue. But in a classical computer, we shrink like is it again a transistor or a switch that has two position. Either is going to be 0 or going to be 1. Now, in a quantum computer, it can be not only 0 and 1, but also can be any combination of these two as well. Let's see if we can consider like a wave. You see the wave can be 0, can be 1, or can be any number between these two. So this is how, because a photon can act also like a wave and also like a particle here, right? But don't worry, don't get confused about it. What do you mean really here? There's been a lot of interesting top conversation around it. And we all know the famous paper that Albert Einstein published in 1905 about the photons and that, but we'll get to that. Actually, I like to discuss that further. But what I mean here is that a qubit can be, for example, a photon can be a qubit. Can be used as a qubit because a photon is like acting like a wave, can act like a wave too. So you see, if I want to show all the position that the photon can take, I can actually show it by this figure here that is called the Bloch sphere. I'm going to talk about it extensively about the Bloch sphere, but sorry, it's not Bloch, it's H at the end. So yeah, the Bloch sphere. So you see that it's like 3 dimensions that we have X, Z, and here also we have Y. So now all the possibilities on the surface of this of the sphere can be a position of that photon. For example, a photon can be here, a photon can be here, a photon can be in this state, photon can be in this state, photon can be in this state, in this state. You see, there are a lot of possibilities that the photon can be in at the same time. So it looks confusing and kind of like doesn't make sense. I get it. We talked about that and you get it later. But anyway, if we want to show the state 0, because of course in a classical computer you also just see 0 or 1. Let me just turn off the other monitor because this pen acting quite strange. Yeah, okay, now it's good. So if you have 0 and 1, but when it comes to the quantum computer, we show the state 0 with this notation. That is like a casket. That I'll talk more about that. And the south pole can be a 1 that we'll just show it with this notation. And now if we want to show the state of a quantum computer, this is the way that I'll show it. It's just a combination of a state 0 and a state 1. Now this alpha and b can be any number between 0 and 1 here, but we just know that alpha plus beta there is going to be 1. For example, if alpha is equals 1, then beta must be 0. But don't worry about it. Just know that the state of the quantum state can be shown with the combination of 0 and 1 like this. Now, if you have 1 qubit, you can represent 2 simultaneous states because 1 qubit can be at the same time both 0 and 1. But if you have 2 qubits, you have 4 states because each of those qubits have a state of 0 and 1. So in total, we have 4 states. So you see the first qubit. Yeah, sorry, this is looking a bit wrong here, but I think it's fine. So the first Yeah, it's like the first state. First qubit can be either 0 or can be 1, and the second qubit can be also 0 or 1. So in total, we have 4 possibilities: 0, 0. So I write it here: 0, 0. The other possibility is 0, 1, 1, 0, and 1, 1. Now, if you have 3 qubits, the total possibility gonna be, each qubit has 2 possibilities. So in total, we have 2 to the power of 3. That is 8 state. If you have n qubits, you can show 2 to the power of n state with that. So n qubits is equivalent to the power of n classical bits. Now think about this. If you have 70 qubits, it's going to be equivalent to 2 to the power of 70 bits. And we don't have a classical computer that can actually store that much of bits. So you see, at 7 qubits, you already have a quantum computer that is more powerful than any classical computer on Earth or any supercomputer on Earth. That's when we call it quantum supremacy, is a point that quantum computers can solve some problems much more efficiently than a classical computer. And one application that actually I didn't talk about, but I want to talk about considering my background, and that's about the cybersecurity itself. Quantum computers can be used for transferring data securely through the quantum optics that we'll have another session about it. Or the quantum computers can actually break the communication that we have right now. For example, the RSA or Diffie-Hellman or elliptic curve, all of them going to be broken by the quantum computers. And there are a lot of topics that I want to talk about it with you, and just stay tuned for that. And let me know if there is any other specific topic that you want to hear during this conversation. So I talked about this already. Let's go to the measurement problem. So there's one interesting thing here, and you might have heard already in a lot of movies and a lot of books about Schrodinger cat. And that's a problem that if you have a cat in the box, I'm going to simplify it. Of course, it's a bit like a longer challenge, but if you have a cat in the box and you have some poisonous material inside that cat, which is like the radioactive material that is keep decaying, because you don't know like how long that decay might take until that poison will be released. So until you don't open the box, you don't know if the cat is alive or is dead. So this is the same problem. This is the same situation that applies to the classical computer. Until you don't measure a qubit, you don't know if that qubit is 0 or 1. So there is a 50% of chance for that qubit to be 0 and 50% chance for that qubit to be 1. So the measurement is hard because we have a decoherence problem. The qubits needs to be cooled down to near 0 Kelvin temperature. Not all of them. There are some types actually that work in the room temperatures too, that we can talk about later. But know that a lot of them needs to be cooled down to near 0 temperature. And if there is a temperature change, actually, it might distort the quantum state and it might collapse. But what does it mean collapse? It means that it's gonna, I told you it's gonna be in either 0 or 1 and a combination of both. Let's say this one. And the moment that you measure it, you see it is on all this state at the same time, right? But the moment that you measure it, either it's going to be 0 or it's going to be 1. So it's going to collapse to one of these two positions whenever you try to measure. And the vibration can impact the quantum too. So that's why you don't want to have any noise around there, because if there is any vibration, any noise, that's gonna do the coherence, which gonna collapse the quantum stability, and that creates an issue because then you have to put it again in a superposition state, and that If it looks complicated, this is the first session. Don't expect it to be to know it right away. Okay. So the secret sauce in this quantum computer is the interference. We have the constructive interference and destructive interference. You see, this is a constructive interference. Let's say you have two waves. This is wave A, this is a photon, and this is another wave. And if you add this up together, and they will sum up, and you see the amplitude will increase. But in a destructive interference, let's say this is again photon A and this is photon B, if you apply them in a reverse order or in the destructive way, they will cancel out each other and the result will be all zero. So we can use this, I'm going to show you later, for finding the right answers. Because as I told you, quantum computers, the qubit can be in multiple states in the same time. I mean, they are in both 0 and 1 at the same time. But you can carefully put them in the constructive way. So whenever they add up together, they boost the probability of measuring the right result. And in destructive interface, you can design the waves in a way that they cancel it out. The wrong answer cancel out each other. So finally, the wrong answer cancel, the right answer is boosted, so you get the right answer. So it's very cool. I know that it doesn't make sense, but we'll get to that, why it is true. You can think about it actually. Here I have an analogy. Think about it like noise canceling headphones. So it's supposed to remove the noise that is unwanted, but at the same time is supposed to boost a noise that is wanted, which is the music that, for example, you're listening to. So this works the same, is trying to destroy or do the destruction of the bad noise and do the boosting of the right noise, which is the music. So what they do actually, again, they put the let's say the photon in the superposition. That when I say superposition, it means super means many. So here I mean many position, which means that again it's both 0 and 1 and in the combination of those, like that wave again. I keep drawing that, so I hope you memorize it better. So you are both 0 and 1 and also all the other values between. And then you apply the interference and finally you measure it and you get the right result, which is very fun. But how? Let's get back to that later. So there is one feature of the quantum computing, and that's no cloning theorem. No cloning theorem means that if you try to measure a quantum state, a qubit that is in quantum superposition, it will collapse again to either 0 and 1. So it means that the moment that you, let's say you are sending a photon from you to your friend, that photon is your key, for example, that you're going to use for encryption. Of course, I'm simplifying here for you to better understand. So this is like let's say the original bit that let's say here is Alice and here is Bob. So Alice decided to send bit number 1 to Bob. I have a video about that. Also, I'll talk about it later. So then make a superposition over these qubits. And on this side, Bob has a technique to recover that actually it was number 1 or bit number 1 that was sent from Alice to Bob. But if someone, an attacker, tries to measure this, they will destroy actually this wave, because it will kind of collapse to either 0 or 1. And then Bob will realize that an attacker here tried to measure it. So they will discard that bit. So what I want you to memorize is that as soon as someone tries to measure this qubit, it will collapse. So everybody will know that somebody tried to measure it or somebody tried to intercept this bit or this qubit. Next, we have a couple of ways that we can create the qubits. Qubits, again, is Q standing for quantum, so they are quantum bits. One way is that we can use actually superconductors. Superconductors that we use them a lot around us for many other applications, including MRI. So the big companies like IBM and Google actually are using superconductors for building quantum computers. The other technique is called trapped ion, and this is used by removing an electron from an atom, and then it becomes more positively charged. So in that kind creates a trapped ion. And big companies like IonQ and Honeywell actually are using this technique. The other way is that to use directly the photons, and PsiQuantum or some other companies are using this. This is not the only way. There are other techniques like neutral atom and a couple of other techniques that have been used. And at the end, we have to see which one going to give us the best result. But just know that there are different materials that have been used for building quantum computers. And still, we have to see finally which one gives us the best result. But of course, as IBM and Google are both of them at the forefront of this competition, superconductors shown better results so far. So you could think about it. I've been asked about a lot of people, and I've seen a lot of people ask this question. Is it possible that we see quantum computers on our office desk or in our home desk? And the answer to this question is that probably not, at least not in the near future. What we're going to see is a combination of both quantum computer and classical computer, because classical computer are doing some tasks pretty well right now. For example, if you want to add up some number, if you want to do arithmetic operation, if you want to do many other tasks, usually this classical computer already are doing a great job. But there are some tasks that classical computer are pretty much bad at, and as we talked about. So we can offload those tasks that classical computers are not good at to the quantum computers and ask the classical computer to do the normal task that don't need that power of a quantum processor. So I talked already about the application, including chemistry, the fertilizers. You see, like Haber-Bosch problem. For example, Haber-Bosch is consuming about 2% of the world's energy. And we know that Haber-Bosch is actually the one that is feeding the world for fertilizer. So what if we can actually decrease that? What if we can decrease it 1%? Imagine how much energy we're going to save by that, right? And AI itself is consuming right now about 1.5 to around 2% of the world's energy. What if we can make it more efficient by optimizing that? The battery technology, finding new materials for lithium sulfur batteries. And what about financial optimization? Let's say if you have a company and you want to see where to invest and which place is which company is the best place to invest your money on, then they're going to help you with optimizing your portfolio. And when it comes to cybersecurity, there is an algorithm that is called Shor's algorithm. And this was introduced in 1994 by Peter Shores. And this is an algorithm that's going to break your internet security. And it's been shown that actually for breaking the algorithm like RSA or elliptic curve and Diffie-Hellman and all these public ciphers that we are using, we don't need actually a lot of qubits. We are talking about a couple of 10,000, around 10,000. The recent paper that has been published very recently, like I'm talking about like 2 weeks ago, has shown that this type of some of these algorithms can be even broken by 10,000 logical qubits, which is actually pretty significant and is a lot of advancement. And that's why Google was supposed to do the transition from cryptography, from public cryptography. They are doing the transition from public cryptography to post-quantum cryptography. I call it PQC because that's what they call it. This was supposed to be done by 2030 for sensitive information, but they are actually doing this faster, and the deadline now is 2029 for Google. So the threat is real. A lot of work's been done in this field, and a lot of great algorithms already been chosen, including the crystal kyber, including like dilithium and many other techniques that are already standardized, and you can use them for securing your internet. But this session is not about cybersecurity; it's just a general introduction, so don't worry about that. So yes. Now there's another interesting features in quantum computer that is called the entanglement. So this means that if two two photons, for example, here photon let's call it photon A and this photon B, if they are very, very far from each other, for example, this is on Earth, and this is on another planet. I'm talking about another planet that is very far from us. Even if they are very, very far, the farthest point in the world, and they are entangled together, if you measure photon A, you immediately know what is the state of photon B, because these two are entangled together. So measuring one of them will immediately tell you what is the state of the other one. So for example, if you measure A to be 0, you immediately know that B is 1. It's very spooky, right? If you think that is spooky, that's what also Einstein was saying. So Einstein called this actually a spooky action at a distance. And it was hard for Einstein actually to accept that, but actually it's been proven now. And we know that if two photons are entangled, but how they entangle it and that, you can do that search, or later on, then in a different video, we get more to that. But if they are entangled, measuring one will give you immediately the state of the other, which is pretty neat. And in that case, I can use it for a lot of applications that you'll see later, including cybersecurity. Thank you so much for watching us today. And next session, we'll get back more to the... I'm going to actually wait before we leave. I want to show you one more thing. There are a lot of great resources out there that you can use, including IBM has IBM Quantum Learning website that teach you a lot of things you already can learn. But I'm going to show you a quick Python demonstration. This is on Qiskit. Let's see how we can build a quantum computer together. But of course, we're running on a classical computer, but still we can get a sense of it. And fun fact, you can even run on real quantum computer, if you have a task like optimization and you want to run it on a real quantum computer, you can actually do it for free. And that's very cool. But we'll get back to that later. Or you can search about it if you are so curious, you don't want to wait for the next session. So here, if we have Qiskit, so I just need to install the Qiskit library. And now I have this command that is quantum circuit 1.1. That is just I am creating one quantum bit and one classical bit. So now if I run this, you see I have one quantum bit and one classical bit. This classical bit I needed for storing the result at the end. But of course, I'm doing everything on the quantum bits. So now here we have a gate that is called an X gate. And this is like a NOT gate that is reversing the bits. For example, if qubit is 0, after passing through this gate, the state of the qubit will be 1. If the qubit is by default 1, after passing through this gate, it will be 0. So whatever the state is here, after passing through this gate, it will be reversed. I'm going to talk about the gates, all of them, hopefully in the second sessions. Don't worry about it right now. I just want to show you what you can do. Now, what I can do, I can do a simulator here. It's called AER simulator. We'll discuss it a lot later, I promise. Don't worry about it. Don't panic. This is very fun. At the beginning, you might see a lot of new things, but actually is a nice challenge. So if I count the number here, and I plot the histogram, you see shows me that you have to run it for a lot of times because interestingly quantum computers are non-deterministic, which means that each time that you run sometimes you might get error, so you have to run it a lot of times until you get the right the final result. Let's say I measured it 1024 times. If in the majority of the cases the measurement says 0, so I assume the initial state was 0. If majority of cases says 1, so I assume that the initial state was 1. But here, as you can see, the majority of the state, actually here, all the states, says that the result is 1. So we know that the outcome gonna be 1. I really hope that's clear, this session. If it's not, just write it in the chat and I will make sure to cover it at the beginning of the next session and we'll discuss it further. Quantum is really fun. This is the future and it's going to be a huge, huge impact. I am sure about it. Much bigger than AI. It started today and be ready for the time that is commercialized and everyone get to the market and you're going to be ahead of the others. Yeah, thanks for watching.